Hello guys, welcome back to my channel. And today I'm not going to be doing an integral. I'm waiting for that sigh of relief. I'll be doing an infinite sum. So and it's going to be a small one. I promise you. Unlike the previous ones that we've explored together. So as always, let's get to it. So we have our problem. Let's call it I. That's defined as the sum from say n equals 1 to infinity of negative 1 to the nth power times the cosine of n all over n squared. So if you want some perspective, I can probably write some terms of this infinite series down. So minus 1, and when n is 1 we just have 1 here, times cosine of 1 divided by 1 squared plus negative 1 squared times the cosine of 2 over 2 squared plus negative 1 to the third power times the cosine of 3 all over 3 squared, and this goes on till infinity. So negative 1 to the first power is just a negative 1 times the cosine of 1 all over 1 squared is just 1. Then negative 1 squared is 1, a positive 1. Cosine of 2 is, we can write it that way, and then 2 squared is 4, minus the cosine of 3 over 3 squared, which is 9, and that goes on till infinity. So as you can see clearly, it's an alternating series, alternating infinite series. And how in the world are we going to actually evaluate this thing? So I'll give you a hint. I want to write the cosine because that's the only thing, because instead of, if we didn't have a cosine over here, this would just be a negative Dirichlet-Eta function, right? The negative Dirichlet-Eta of 2, right? So we need to write the cosine in uh, in a form that makes evaluation very easy. Evaluation of this infinite series easy. So I mean, it's valid to wonder there must be some compact form to write the cosine of of a number, in considering the vast ocean of mathematical literature that's available. I mean, Euler, Lagrange, Laplace, Fourier. Many people have, many great mathematicians have lived, and I'm sure they must have done some great work, right? So I'm going to show you an exponential definition of the cosine function on another page. So see you there. So we should, I think, first refer to Euler's formula, which is e raised to I theta is equal to cosine of theta plus I times sine of theta, because that's the only formula that relates trigonometric functions like the cosine and the sine to something like an exponential function, which is way easier to calculate, not exactly calculate, but to work with, because if you have done some calculus before in courses, read textbooks or something like that, differentiating and integrating the exponential function is one of the easiest things to do. I mean, it's literally child's play. So great. There's this beautiful identity that we have, but how can we single out just the cosine, because we want an expression for the cosine. So we have this e raised to I theta is cosine of theta plus I times the sine of theta. What if we take a negative angle? Say we take e raised to I times negative theta being equal to cosine of negative theta plus I times the sine of negative theta. Well, that you can just take the negative outside. E raised to negative I theta is nothing but cosine of a negative angle is always a positive cosine. So cosine of negative theta is just cosine of theta, and the sine of a negative angle is a negative sine of the of that angle. So minus I, so sorry, there should be a minus here. So negative I sine of theta. So well, why don't we add these two equations together? So e raised to I theta equals cosine of theta plus I times the sine of theta. So we're basically going to add these two together. We get e raised to I theta plus e raised to negative I theta equals, well, the I sine thetas cancel out, right? And we have 2 times the cosine of theta. So basically 2 times the cosine of theta is nothing but e raised to I theta plus e raised to negative I theta. Why don't we divide both sides by the by 2? So we obtain cosine of theta is equal to e raised to I theta plus e raised to negative I theta over 2. So that's basically a compact form of the cosine that is way easier to work with, and you will see just in a minute why when we plug it in our original problem. When we plug it in our problem, you just see why this is way useful. So we had our original problem I as the sum from n equals 1 to infinity of negative 1 to the nth power times the cosine of n all over n squared, and we just said that uh, the cosine of n is nothing but e raised to I times that angle n plus e raised to negative I times that angle n over 2. So why don't we substitute all this in over here? So we have I being equal to the sum from 1 to infinity of negative 1 to the n over n squared, and we have e raised to in plus e raised to negative in all over 2. Now we can legitimately multiply um, inside the bracket, basically expand this thing. So we have negative 1 to the n times e raised to in over 2n squared plus the sum from n equals 1 to infinity. So I've basically split them into two different sums. So the sum from negative 1 to the nth power times e raised to negative I times n over 2n squared. Well, we have a constant of half in both of these sums, so we can just plug it out. So we have the sum from n equals 1 to infinity, negative 1 to the nth power times e raised to I, the whole thing raised to n, right? Because if you use your properties of exponents on this, multiplying powers is basically raising the entire thing to that power over n squared, and I'm going to do the same thing over here. So we have the sum from n equals 1 to infinity of minus 1 to the n, and we have e raised to negative I but the whole thing raised to the nth power over n squared. So what I'm going to do now is I'm going to take the negative 1 and the e raised to I under a common power. So I have half times the sum from n equals 1 to infinity of minus e raised to I, the whole thing raised to n, divided by n squared, plus the sum from n equals 1 to infinity. I'm going to do the same thing over here. Negative e raised to negative I, the whole thing raised to the nth power, divided by n squared. Now both of these have some familiar form, right? What's the familiar form? If you wanna uh, do some brain activity, you might want to pause the video and guess what form this is. So in case you didn't get it, I'll remind you that we had a dilogarithm of x being defined as the sum from n equals 1 to infinity of x to the nth power over n squared. And in our case, instead of our x, we have a negative e raised to I over here, and we have negative e raised to negative I over here. So basically it's basically a sum of two dilogarithms. So we have our I now being equal to half times, well, using the definition of the dilogarithm we obtained, this is nothing but the dilogarithm of negative e raised to I plus the dilogarithm of negative e raised to negative I. But I still want to express this in a slightly different way, and you'll see in a minute why. So I'm going to write this as it is, negative e raised to I, dilogarithm of negative e raised to I, plus the dilogarithm of 1 over negative e raised to I, because I'm writing a negative exponent in the denominator, and it becomes a positive exponent. Basic properties of exponents. Now why is this useful? Because we have an interesting identity in the world of dilogarithms that is basically can be seen as the sum of a dilogarithm plus the dilogarithm of the reciprocal of the argument. So say we had an argument initially z, so the dilogarithm of z plus the dilogarithm of 1 over z is equal to negative pi squared over 6 minus half of natural log squared of negative z. I'll put this slight dash here so that you don't confuse that with a 2. So this is basically the sum of dilogarithms which with reciprocal arguments, and that's exactly what we have here, right? We have negative e raised to I and then the reciprocal of that, 1 over negative e raised to I. So this is very useful for simplifying and obtaining a closed form for our answer. So now I is equal to half because it's outside the bracket, and then I'm using this formula now to write this as negative pi squared by 6, because this is a constant anyways, minus half of the natural log squared of negative z. And what was our z? It was negative e raised to I, so negative of that, so negative of negative e raised to I is nothing but e raised to I and we can multiply everything. Now we obtain half times 1/6 is 1/12. So negative pi squared by 12 minus 1/4 of the natural log of e to the I, but the whole thing squared, because basically natural log squared is the natural log of a term squared with itself, multiplied with itself basically. Now for the purpose of simplification, we can also use this great property of logs in general. Say you have the natural log of a to the power of b. This can be written as b times the natural log of a. So the powers can be brought down and multiplied outside with the natural log of the base term. So here we have the power I, so that can be brought down. So this becomes negative pi squared by 12 minus 1/4. And then when you bring the power I down, you have just I times the natural log of e, the natural log of e, but the whole thing squared. And the natural log of e is 1, because the natural log is log to the base e. So e raised to the first power is e, right? That's why this thing is 1. So we have negative pi squared by 12 minus 1 over 4 I squared. And since we know that I is nothing but the square root of negative 1, it's an imaginary unit. So we finally obtain negative pi squared by 12. Negative and a negative make a positive. So plus 1 by 4. So that's a pretty interesting result, because we just randomly get this pi squared term over here. So it's quite fascinating. So in the end, to sum whatever we did in this video, say we had I, which was defined as the sum from n equals 1 to infinity of negative 1 raised to the nth power times the cosine of n over n squared. We used the exponential definition of the cosine, and then the dilogarithm that we obtained, and then the identity of the dilogarithm, to finally get an expression of negative pi squared over 12 plus 1 by 4, which is approximately negative 0.572467. Obviously it's recurring because pi is irrational and transcendental. Now, what always fascinates me about these infinite series is that if they converge, you get this finite product. I mean, it's a recurring decimal, but we can say it's a numeric actual value that you can assign. It's like adding some stuff infinitely. Here that stuff was alternating, but adding some stuff infinitely to result in some finite value. Here the value is negative, so it probably seems that the negative parts of this infinite series dominated the positive part, because it's an alternating. The sign changes per consecutive term. But all in all, it's a really neat result, especially in this form. And we also can't ignore the fact that this was probably one of our shortest series evaluation videos, because it was pretty easy once we plugged in the definition of the cosine in terms of those exponential functions using Euler's formula. Everything just fell into place, and it's pretty strange, because we keep running into this dilogarithm function since the first video that I used it in. It's been part of our integral and infinite sum videos now. So we need to give the dilogarithm a little bit of credit too. I mean, we definitely used the identities, but it was the identities of the dilogarithm function that's important. So that's it for this video, guys. Stay home, stay safe. Peace out.